A vector is a quantity having both magnitude and direction. Vectors may be represented by using directed line segments or arrows. The tail of the arrow is called the initial point of the vector. The head of the arrow is the terminal point. In this chapter we have many keywords such as magnitude, unit vector, and others. We also learn addition and subtraction of vectors. The scalar product of two vectors and is denoted by a dot b. There are three rules for the angle between two vectors. First rule is if two vectors A and B are parallel and in same direction, the angle is 0 degree. Second rule is for unlike parallel vectors, the vectors are parallel but in the opposite direction and the angle is 180 degree. Third rule is if two vectors A and B are perpendicular, then the angle between the two vectors is 90 degrees.
In our everyday life, we use the concept of vector. As example, during the crosswind. Crosswind is a wind that blows in a direction perpendicular to the trajectory you are traveling in. When a plane finally lands, it sometimes struggles due to crosswind. However, the pilot can use the vector to determine the resulting speed and direction. Another example is in gaming. In gaming, vectors are important to store position, direction, and speed. The position vector indicates the distance of the object, while the velocity vector indicates the required time or force that we should transmit, and the direction vector indicates in which way we should apply the force.
The last part of 5.4 is between one line and one plane, where you need to find the angle theta between line and plane, as well as the point of intersection between the line and the plane. So let's start with the angle between a line and a plane. Let's say this is your plane and you have a line going through your plane. And hence you're going to have a coordinate, which is actually the point of intersection where your line intersect the plane. So let's say I'm going to call that coordinate x, y, and z. So I want to find the angle between line and plane. So this is the line and this is your plane, and hence the angle theta between line and plane is here. So remember that the angle theta is the angle between line and plane. Now let's look at the line L. The line L will have its own direction vector v, and the plane will have its own normal vector going upward like this. And I'm going to call the angle between the normal vector and the direction vector v as alpha. So as we can see here, the angle theta is not the same as the angle alpha. Alright, it's different from what we have in planes before this. But we do know that since this is normal vector, therefore the angle right here is 90 degree. And hence 90 degree is actually angle alpha plus angle theta. And hence the angle theta that we need to find is actually 90 degree minus alpha, where alpha is the angle between the normal vector and the direction vector. So step 1 is to find alpha by using the dot product. Alpha is cos inverse v dot n divided by magnitude v times magnitude n, and hence we can find theta. So why do we find alpha first? Okay, note that the dot product, which is a dot b equal to magnitude a, magnitude b, cos theta, and you can use this to find theta, which is cos inverse a dot b divided by magnitude a, magnitude b. So note that this formula can be used when you have vectors. which is vector A and vector B. Okay, so the angle theta is between vectors A and B. The angle is for vectors. Okay, so that's why for this formula, we need to use the vector V and N. And we know that between the vector V and vector N, we have the angle alpha. That's why we can use the dot product to find the angle alpha. And we're gonna use this alpha next to find the angle theta that we want, which is theta is the angle between line and plane. You also need to find the point of intersection between line and the plane. So let's look back at the diagram. We know that the point of intersection is a point. Therefore, it's going to have the coordinate x, y, and z. And in order to find these coordinates, I need x, y, and z from line and plane. So for line, you can have the equation for x, y, and z from parametric equation. And for plane, I need to have the x, y, and z from the Cartesian equation. So you must see x, y, and z in both equations of line and plane. Next, you're going to solve these two equations to find the value of your parameter t, and then you can use that to find the values of x, y, and z. Example 15, question 1. I need to find the vector equation of a line containing a fixed point 2, 1, negative 2. So this is my line L, and it passes through the point 2, 1, negative 2. And the line is in the direction I minus j minus k. And we know that whenever you have the word in the direction, this means that this vector right here is the direction vector v, which is 1, negative 1, negative 1. At the same time, this line is perpendicular to the plane that passes through 4, negative 2, negative 1. So this line is 90 degrees to a plane. And this plane passes through this point. So let's say we have a point 4, negative 2, negative 1 on the plane. So I need to find the equation of this straight line first. So we know that for the line, the formula is r equal to a plus tv. So the vector a comes from any fixed point on the line, which is this one. So vector a is 2, 1, negative 2. Next, I need the vector v, which is 1, negative 1, negative 1. And this is the vector equation of the straight line. Next, we also need to find the point of intersection between line and plane. So this is the line, and this is the plane. And hence, the point of intersection will be here, where we will need to find the coordinate x, y, and z. So I need x, y, and z from both plane and line. So from line, I need the parametric equation. And this will be my first equation. Next, for the plane, I also need the Cartesian equation, since it has the x, y, and z. So let's find r dot n equal to a dot n. Note that the normal vector of the plane, which is n, is parallel to vector v. Therefore, the vector n is actually the vector v, which is 1, negative 1, negative 1. And for vector A, it comes from any fixed point on the plane, which is 4, -2, -1. Dot again with the normal vector, which is 1, -1, -1. Therefore, the right hand side will be 7. And hence, this is the vector equation for the plane. But we need the Cartesian equation by letting the vector r to become vector x, y, and z. And we will get x minus y minus z is equal to 7, and this will be my second equation. So as you can see, here I have x, y, and z, and here I also have x, y, and z. So I can substitute equation 1 into equation 2. So now we can substitute the value of t into equation 1 to find the coordinate for x, y, and z. And hence, x is 10 over 3, y is -1 over 3, and z is -10 over 3. And that will give you the point of intersection between the plane and the line.